Good morning, students. Welcome back to this data structure class again. In the last few classes, we have been discussing about list, both list using array and a list using pointer. Now we are going to discuss about application of list. Where we can use this list. From the beginning, I have been telling you that your data structure can be analyzed at three levels. One is logical level, implementation level, application level. The logical level is answering the question of what is the particular data structure is. Then implementation level is how we are going to implement such a data structure. Then application level is where we are going to use that data structure. So for stack, we said a stack is a abstract data type in which elements are processed in the last in first out order. That answers the question of what. Then implementation, how we are going to implement. We have demonstrated the way to implement such a data structure. Then where we are going to use to convert an infix expression to postfix expression, a stack can be used. That is one of the applications that we have seen. Like this, the linked list, what is the logical level? It is a homogeneous collection of elements with a linear relationship between them. Then implementation level, how to implement such a data structure, that we have demonstrated in the last few classes. Now we go for the application level, where to use. This is, we can use a list to add two polynomials. We can use both list using array and a list using pointer to add two given polynomials. Okay. In what way polynomial is related to linked list? Is it possible to express a polynomial using a linked list? First of all, what is a polynomial? It is not an equation, rather it is an expression made up of operands and operators, operands connected by operators. It is an expression in which the operators connect operands. Okay. For example, you take your quadratic equation ax squared plus bx plus c equal to 0. If you put equal to 0, then it is a equation. Just avoid that equal to 0, then it is ax squared plus bx plus c. That is a polynomial, where a, b, c are coefficients and 2 and 1 are exponents. Okay. Then how we can express such a polynomial using a linked list? It is very much possible. Okay, we are going to demonstrate it now. Okay, now you look at this picture. This list is an ordinary list. A list is having a data field and a pointer field. Every node is having a data field. This is the data field and this is the pointer field. This every node is a self-referential structure. So in the self-referential structure, there are two members. One member is this data member and another member is a pointer member. It is not necessary that a self-referential structure should have only one data member. It can have two members. It can have two members. Now, let us have one more data member here. One more data member. One member for the coefficient and another member for the exponent. Another member for the exponent. Okay. By that way, we can express a polynomial as a linked list. Okay, I see. I gave you one example. Now look at this polynomial. 10 power 10, 10x power 10 plus 8x power 8 plus 6x power 6 plus 4x power 4 plus 2x power 2. This is a polynomial. How I am going to express it as a linked list? You see, this is a linked list. It has three members. These two are the data member and this is a pointer member. It should have an external pointer. Then this is the coefficient field, this 10. Okay, this coefficient, this is here. Then this exponent, this is the exponent. Okay, so 10x power 10, 8x power 8, 6x power 6, 4x power 4, 2x power 2. See, you see, this is the first node, second node, third node, fourth node, fifth node. Okay. And the last node is not pointing anything more. So the first node is related to the first term of the polynomial, and the first node is pointing the second node. So this term is pointing this term, and this term is pointing this term, and this term is pointing this term, this term is pointing this term. Like this, we can express a polynomial as a linked list. Then how can we add two polynomials like this? How can we add two polynomials? Okay. Supposing I have another polynomial. Let us take 9x power 6x power 10. 6x power 10 plus 3x power 8, 3x power 8 plus 2x power 6. This is another polynomial I am having. Okay. In that case, this will be 6 and this will be 10 and this will be 3 and this is 2. This is 2. Then these things are nothing. These things are nothing. They don't have corresponding terms. Now, how I am going to add these two polynomials? There will be a pointer, maybe external pointer P1 for the first polynomial, P2 for the second polynomial. Okay, and this one is P1 reference coefficient, this is P1 reference exponent. P2 reference coefficient, P2 reference exponent. Okay, maybe I can have one more auxiliary pointer, T1 for the first polynomial, T2 for the second polynomial. Okay, then I will have T1 reference coefficient plus T2 reference coefficient. I will add these two. Now, now let us say this is T1 reference, T2 reference. T2 external pointer for the first polynomial, T2 external pointer for the second polynomial. Let there be a external pointer for the resultant polynomial, that is T3. Okay, this T3 coefficient is nothing but T1 coefficient plus T2 coefficient. So T1 coefficient is 10, T2 coefficient is 6. So 10 plus 6 is equal to 16. So T3 coefficient is equal to 16. Then the exponents are same, 10, 10. So the T3 exponent is also equal to 10. So this T3 exponent is equal to either T1 exponent or T2 exponent. Then I will move my T1 from this node to this node, T2 from this node to this node. When I move that, this is T2 coefficient, T1 coefficient, this is T2 coefficient. So I will move my T3 also from here to here. Okay. So 8 plus 3 is equal to, it will be T3 coefficient now is equal to T1 coefficient plus T2 coefficient, it will be 11. And the exponent is either one of the first polynomial or second polynomial. Then I move my pointer from this node to this node, T1 from this node to this node, T2 from this node to this node, then T3 from this node to the next node. Okay, it will be T3 coefficient is equal to T1 coefficient plus T2 coefficient, that is equal to 8. Then T3 exponent is either one of these two exponents. Okay, then you see there is no term with this. All the elements of second polynomial are considered. I have to select the, I have to copy the remaining terms of the first polynomial to the resultant polynomial. So T1 is moved from here to here, T3 is moved from here to here. This is nothing but 4x power 4. Then okay, then T1 is moved from here to here, T3 is moved from here to here. It is nothing but 2. It is nothing but 2. Okay. So like this, we can add two polynomials. Okay. So this is the resultant polynomial. Okay. This is the way. So simply said, but when it comes to implementation, we have to take into consideration several cases of addition. Okay. Here you see this polynomial is having 1, 2, 3, 4, 5. That is 1, 2, 3, 4, 5. And this polynomial is having only 3 terms, 1, 2, 3, 1, 2, 3. So the number of terms might be same or different when you try to add two polynomials. That is, when you try to add two polynomials, there are several cases of adding two polynomials. That is, the first case is polynomial 1 and polynomial 2 are having the same number of terms. First polynomial is having 5 terms, second polynomial is having 5 terms. Then case 2 is the corresponding polynomials, corresponding terms of the polynomials might be different. So in this case, you see is 10x power 10, then it might be 6x power 9, 6x power 9. See, like this, although the number of terms of the two given polynomials are the same, their exponents might differ. Exponents might differ. That is the one. Then second category, third category is first polynomial is having more number of terms than the second polynomial. Like this, in this case, the first polynomial is having two more terms, whereas the second polynomial is having only three terms. So when you try to add, the logic for that is somewhat different. Then the third, for next category is the first polynomial is having less number of terms, the second polynomial is having more number of terms. Okay. See, here once all the terms of the second polynomial are considered, we just copied the remaining terms of the first polynomial to the answer polynomial, result polynomial. Like this, when the first polynomial is having less number of terms and the second polynomial is having more number of terms, after considering all the terms of the first polynomial, the remaining terms of the second polynomial should be taken to the output. That is the thing. So these are the various sub cases involved when you try to add two polynomials. So the logic that you are going to write should take into consideration all these cases of polynomial addition. Okay. Now we try to implement a addition of polynomials using linked list. Okay. As you know already, I need a self-referential structure. Okay. I call that as struct poly. Struct poly. Well, the exponents only should be integers in a polynomial, but the coefficient can be either a integer or a coefficient can be either integer or a float value. So my first term of the self-referential structure is a coefficient. I treat it as float coefficient. Okay. The second term of my self-referential structure is the exponent. Exponents are always integer in a polynomial. So, okay. On the third term, this is a pointer member. Okay. So I call that as poly star next. Poly star next. Okay. This is my self-referential structure. Okay. Then see, I need a, first of all, I will be having a empty polynomial. In the empty polynomial, I will be adding one term. Then I will be adding another term like this. For example, in this term, there are 5 things. Then I want to add one more term means then maybe 1x power 1 means then from here, from this pointer field, a new empty node is created and the new empty node I will be adding 1 and 1x power 1 in that then I will make the next field as null. So I need a mechanism to insert a value into the polynomial. Okay. For that I write a very small function void insert term. Void insert term. Okay. And it needs 3 parameters. They are float coefficient and exponent and a pointer number. Our pointer type is this one, reference type. Reference type. Okay. And this one is tail reference next equal to new poly. See, if at all I want to add 1x power 1 here, from this pointer, remember, I create a new node, there I insert it. That's why I use this tail reference next is equal to new poly. Okay. Then I set tail is equal to tail reference next. Then tail reference coefficient is equal to coef. Tail reference next is equal tail reference exponents. Okay. Okay. Then that's all. So this is one function I need to insert a value into the. Okay. Then I need a polynomial to read a polynomial. Okay, I need a function to read this polynomial 10x power 10 plus 8x power 8, 6x power 6, 4x power 4 plus 2x power 2. So next I am going to write a polynomial. Mind that you see here, the exponents are in the decreasing order. Always in a polynomial, the exponents will be in a decreasing order. So here also, I treat every polynomial are having a decreasing exponent terms. Decreasing exponent terms. Okay. Then, when do I stop reading the polynomial? Once I try to read a exponent which is bigger than the previous exponent term, there I will stop. Or the coefficients of a polynomial cannot be zero. So when you try to read a zero coefficient, there also you stop. So these are the two instances wherein we stop accepting more terms of a polynomial. Okay, or reading the polynomial. What are the two cases? When I try to read a zero coefficient, or when I try to read a exponent which is bigger than the previous exponent. So with that understanding, I will write a function that reads a polynomial. Okay. Reading polynomial. What polynomial to read? It should have an external pointer. I call that as result. Okay. And the read polynomial should be given as given to the actual parameter. So I have this reference. Okay, here the parameter is this one. Okay. Then I need a variable that tells whether accepting the polynomial is over or not. So I have one variable called over. Okay. Then I need a variable to accept the coefficients of a polynomial. Okay, then I need a variable to accept the exponents of the polynomial. So okay, then I need one more. Okay, so we are going to develop this reading polynomial. So for convenience sake, I take one very large coefficient term, very large exponent term, so that the subsequent exponent terms will be less than that exponent. So maybe I have last exponent equal to some, maybe some like this. So we have a very big term. Then what happens because of this statement? Result is equal to new means a dummy polynomial term is created and that will be pointed by the variable result. That's what happens. Okay. Then I make a extra connection for this one also. That is tail is equal to result. Tail is equal to result. Okay. So then do get the value of the coefficients in get the value of the coefficient. Okay. I told you in the beginning, when you try to read a zero coefficient, then you are going to stop. Okay. So if the red coefficient is equal to 0, then you stop accepting the terms. So if is equal to 0, over is equal to 0, over is equal to 1, over is equal to 1. Okay. Else okay. If over is equal to 0, if not, that is if is equal to 0, that is if the accepting polynomial, that is reading polynomial, is not yet over, if not yet over, then you accept the exponent of the polynomial. Okay, so Cn exponent. Okay, I told you that the red exponent should be compared with the previous exponent. The previous exponent is equal to 10,000 we have, right? Okay. So if the value of the current exponent is bigger than the value of the previous exponent, then you stop. Okay. So also the exponent cannot be negative. Okay. So if uh, these things need more coding. We are shortage of time for this recording. We will do the remaining coding in the coming class. Okay. We will see in the next class. Okay.